As a warm-up exercise, print the powers of 2 from 1 through n, inclusive. For example, 2 to the power 1 is 2, 2 square is 4, 2 cube is 8, 2 to the power 4 is 16, and so on. We can use the exponentiation operator to compute these values. We can now write the code. We will start from 1 and go up to n and print the values. Let's write a program to compute a to the power b without using exponentiation operator. A to the power b is called the exponent, and a is the number such as 2, 3, etc. So we can compute 2 to the power n, 3 to the power n, etc. Pause the video now and write the code for iterative solution. Let's look at the iterative solution. The power method takes two parameters, a, b, for the number and exponent. The return value will be an integer, so we will return the answer variable. Before we can enter the loop, we need to initialize the result variable answer to 1. Because we will be multiplying values to accumulate the final value. We need to know the terminating condition for the loop before we do repeated work. In this case, we will iterate as long as b is greater than 0. Because we will reduce the value of b in each iteration by 1 to move towards the terminating condition. We need to accumulate the value in answer variable by multiplying its previous value with the value of a. This is a product accumulator. The time complexity is O of n and space complexity is O of 1. Let's now implement the recursive version of power function. We want to calculate b to the power of n. We can expand it like this. B is base b. It's a real number. N is the exponent. It's a non-negative integer. The first approach calculates powers in linear time. What is the size of the problem? Exponent n grows as runtime of algorithm increases. The result would require more multiplications. The exponent n is the size of the problem. What are the base cases? Base cases are trivial instances of the problem with minimum size. In this case, n is greater than or equal to 0. The smallest instance is b to the power 0. So n equals 0 is the base case. Let's draw the recursion diagram for this example. The inputs are b and n. The result is b to the power n. We can reduce the size of the problem by 1 unit. The result of the subproblem is b to the power n minus 1. What do we need to do in the combine step to the result of the subproblem to get the result of the original problem? We need to multiply it by b. The function for the original problem is f of b n. The function for the subproblem is f of b comma n minus 1 equals b to the power n minus 1. We assume to know the solution to this function. We can now write the code. The power method takes two parameters, b and n, the number and the exponent. In the base case, we check if n is 0. If so, we return 1. In the recursive case, we make a recursive call. We reduce n by 1 unit and multiply the result of the subproblem by b. The time complexity is linear with respect to n. We need to allow negative integer exponents. What is the size of the problem? The size of the problem is absolute value of n. We reach the base case when n equals 0. For the recursive case, n is less than 0. Let's look at the problem decomposition step. When n is negative, reduce the size of the problem to ensure subproblem gets closer to the base case. To move towards the base case, we need to increment n. Let's look at the recursion diagram for this example. The inputs are b and n. The result for the original problem is b to the power n. In the reduction step, we increment n by 1 to move towards the base case. The result for the subproblem is b to the power n plus 1. In the combine step, we need to divide the result of the subproblem by b. The result of the subproblem must be divided by b to obtain b to the power n. The recursive case can be expressed by the function. We are now ready to look at the recursive implementation. The method signature is the same as before. The base case is also the same as before. We add a new else condition to check if exponent is positive. If so, we do what we did in previous solution. If the exponent is negative, we make another recursive call. The value of n is incremented in this case to move towards the base case. Let's look at another approach. We will solve powers in logarithmic time. In the problem decomposition stage, we will consider a subproblem of half the size. The assumption is that n is a non-negative integer. We have two cases. Case 1 when n is even and case 2 when n is odd. Let's look at the recursion diagram. For case 1, when n is even, inputs are b and n. The result is b to the power n. In the reduction step, we will reduce the size of the problem n by half. The result for this subproblem is b to the power n by 2. In the combine step, we need to square the result of the subproblem to get the result for original problem. Let's now look at the recursion diagram for the case when n is odd. The inputs and results are the same as before. In the reduction step, we need to subtract 1 from n and divide it by half. The result of this subproblem is b to the power n minus 1 by 2. In the combine step, we need to square the result of the subproblem and multiply by b to get the final result. We can now define the recursive function. It has one base case and two recursive cases. We can now translate the recursive function to code. The base case is the same as before. The first recursive case handles the even numbers, where we reduce the problem size by half and square the result of the subproblem. The second recursive case handles the odd numbers. The code is a direct translation of the mathematical function. Sign up for your free coaching call by going to codinginterview.coach.